This video is a visual guide on engineering two-photon absorption, translating molecular dynamics into optimized photochemical yields. The life cycle of a two-photon excitation involves three phases. Phase 1 is environmental and molecular modulation. Phase 1 includes solvent polarity, which dictates baseline energy states. In polar solvents, induced charge separation can break symmetry, potentially reducing the absorption cross-section. Intermolecular alignment can either multiply or quench absorption. Enhanced alignment, like J aggregates, increases the effective transition dipoles and amplifies the cross-section. Vibronic coupling smooths the absorption profile. Vibronic mixing allows electronically forbidden transitions, and Frank-Condon factors transform sharp theoretical lines into broad bands. Phase 2 is resonance amplification. Double resonance designs amplify the cross-section, with the transition amplitude surging when intermediate states approach resonance conditions. The cost of resonance is competing absorption. One photon absorption, or OPA, can deplete pump laser energy, and excited state absorption, or ESA, can intercept the photochemical process. Phase 3 is excited state dynamics, which maps the ultrafast relaxation cascade. After two-photon absorption, molecules undergo internal conversion down to S1, where competing fates determine the outcome. The Photoinitiator paradox demands strict trade-offs. Designers must balance high raw absorption capability with a high photolysis yield and efficient intersystem crossing. Molecular engineering levers for photochemical yield include solvent polarity, vibronic mixing, double resonance, and managing excited state lifetimes. This video explores the zero shrinkage unicorn and TPP resins. We will discuss why purely radical acrylates always contract, and the pragmatic chemical pathways to achieve metrology-level near-zero shrinkage. The myth is verified zero volumetric shrinkage under purely radical acrylate polymerization. The reality is that volumetric shrinkage is chemically built in, with typical resins shrinking in the few to 10% range. Reaching no shrinkage requires active compensation mechanisms, such as ring opening expansion or high filler loading. The physics of chain growth intrinsically guarantee contraction. Converting C equals C into CC pulls molecules together, which is an unavoidable physical constant for volumetric reduction. Shrinkage compensation relies on a mechanical counterforce. Structures that reduce shrinkage use an additional ring opening pathway to counteract the inherent contraction of the acrylate groups. Ring opening is stronger under cationic or mixed mode initiation than radical only. Pathway A is the spiro-orthoester, meth acrylates. This design incorporates spiro-orthoester chemistry directly into an acrylate backbone for expansion. However, under radical initiation, this yields mostly vinyl polymerization with minimal spiro ring opening. Strong expansion requires ionic initiators. Pathway B is vinyl cyclopropane additive blends. This component is not an acrylate itself, but is blended into acrylate networks and is radical curable. Shrinkage reduction is directly tied to the ratio of ring opening versus cyclobutane formation during photoinitiated radical polymerization. The closest to zero benchmarks utilize non-radical pathways. Negligible shrinkage, around 0.21%, is achieved via spiro-orthoester chemistry in a cationic catalyzed polyaddition molding system. Near zero shrinkage, below 0.5%, is achieved through newly designed spiro-orthocarbonate featuring oxetane groups, co-polymerized with epoxy resins. Verified near-zero numbers exclusively exist outside strictly radical acrylate-only systems. This spectrum shows the volumetric shrinkage ranging from standard pure radical acrylates to the theoretical pure radical unicorn of 0.000%. Reduced shrinkage is achieved with radical plus vinyl cyclopropanes, or ASOE/MASOE. Near zero is achieved with mixed mode / cationic, ring opening compounds and epoxies. The pivot for TPP is to redefine the goal. Instead of forcing 0.000% in a pure radical acrylate network, aim for net shrinkage below the metrology noise floor, which is less than 0.5%. The methodology involves utilizing shrinkage compensating components and embracing mixed mode initiation to actualize the expansion counterforce. This video explores the ultra-fast chemical kinetics of two-photon-induced polymerization mechanisms, tracing the process from femtosecond photon absorption to the formation of solid polymer networks. The reaction follows a timeline beginning with two-photon absorption, leading to the photoinitiator excited state and radical generation. These radicals then add to the acrylate double bond, resulting in a solid polymer network. Femtosecond laser pulses deliver localized near-infrared photons to the acrylate resin. The high photon density at the focal point drives initiation localization. Photoinitiators transition to excited states via intersystem crossing, particularly prevalent for heavy atoms or aromatic ketones. The resulting singlet 1 and triplet 1 populations undergo the same chemistry as one-photon UV processes. Excited ketones can cleave bonds, known as type 1 or Norrish 1, yielding 2 radicals. Alternatively, they can abstract protons in a type 2 reaction, which involves hydrogen abstraction from a donor like an amine. Initiation efficiency in two-photon polymerization relies on both absorption and photolysis. Efficiency is measured by the action cross-section, which includes both absorption probability and photolysis quantum yield. Substitutions can significantly increase the photolysis quantum yield. For example, acyl phosphine oxide exhibits a quantum yield of nearly 1, much higher than benzoin. Free radicals trigger rapid acrylate chain propagation. Generated radicals initiate free radical polymerization by adding to carbon-carbon double bonds, which creates new radicals that propagate the chain. Focal voxels experience extreme radical concentrations, ranging from 10 to the power of -6 to 10 to the power of -3 mol per liter, resulting in exceptionally fast polymerization due to this localized density. The quadratic intensity dependence confines the reaction to the focal volume, ensuring that polymerization only occurs above the critical polymerization threshold. Competing kinetics suppress the reaction outside this area. Multifunctional acrylates act as cross-linkers, bridging multiple propagating polymer chains. This process, called gelation, transforms the exposed voxel into a covalently linked solid three-dimensional polymer network. This diagram summarizes the complete two-photon-induced polymerization pathway, from two-photon absorption and quadratic confinement, through radical generation and chain propagation, to the formation of a covalently linked solid network. Welcome to this video on the mechanism of donor-acceptor and TADF initiators in two-photon polymerization, or 2pp. We will trace the life cycle of 2pp from initial nonlinear optical absorption to final radical chain growth. Two-photon absorption provides extreme 3D spatial resolution, confining excitation and initiation. However, photon absorption alone is insufficient. The excited molecule must undergo subsequent chemical reactions to start polymerization. Donor-acceptor chromophores act as highly efficient optical antennas. Push-pull electronic structures increase charge transfer character and nonlinear optical response. Extending conjugation in a quadrupolar architecture drastically widens the 2pp fabrication window. High two-photon absorption is strictly optical, but reaction chemistry dictates the final outcome. The fluorine paradox shows that a lower optical absorption cross-section can lead to a lower polymerization writing threshold due to superior reaction chemistry. TADF donor-acceptor molecules enable critical reaction time through spatial separation of molecular orbitals. This spatial separation reduces the exchange interaction, causing an ultra-small singlet-triplet gap. Reverse intersystem crossing, or RISC, recycles states to produce delayed fluorescence on a microsecond timescale. This process thermally upconverts triplets back to singlets, extending the lifespan of the excited state. TADF keeps the excited state chemically viable until it encounters a co-initiator. Unlike standard initiators, the TADF state persists long enough for bimolecular electron transfer chemistry to occur. Productive radical formation branches into 2 primary mechanistic pathways after reaching the excited charge transfer state. These are type 1, direct cleavage, and type 2, photoreduction with co-initiators. Type 1 initiators rely on direct bond cleavage and rapid fragmentation. The molecule contains a weak bond that breaks upon excitation. Subsequent decarboxylation prevents radical recombination, driving initiation efficiency. Type 2 initiators act as photosensitizers in continuous photoreduction cycles. The DA or TADF chromophore is continuously regenerated through an oxidative and reductive direction, vastly improving overall efficiency. Recent breakthroughs identify the long-lived triplet charge-separated state as the reactive workhorse. DA-TADF molecules rely on these long-lived states to drive radical generation, unlike conventional photoinitiators. Generated radicals convert the liquid monomer resin into a solid cross-linked network. The initiating radical adds monomer, creating a propagating chain. The reaction stops via recombination or disproportionation. The complete mechanistic pathway includes 4 phases: optics, quantum, chemistry, and result. This traces the process from the laser pulse to the final solid 3D structure through radical generation and acrylate propagation. We are exploring the quantum mechanics of TADF radical photoinitiators beyond their use in OLEDs. TADF mechanisms enable upconversion from triplet to singlet states using ambient thermal energy. In photoinitiators, this energy crossing allows diversion from light emission toward high-energy reactive states. In OLED design, the goal is rapid harvesting and maximizing reverse intersystem crossing, or RISC, from the triplet to the singlet state. In photoinitiator design, the goal is the opposite: to delay RISC, to allow time for chemical work and radical formation in the triplet state. Radical initiation is a branching ratio problem involving coupled excited state surfaces. The initiation quantum yield depends on the relative rates of chemical work versus other decay pathways, such as RISC. Quantum mechanics governs every rate constant in this process. Spin population is meaningless without the correct reactive state. The chemically reactive state is rarely a pure locally excited state. Instead, it is often a mixed charge transfer, or long-lived charge-separated state, which is our target for high reactivity. Reverse intersystem crossing, RISC, drains the reactive triplet before chemistry can occur. If the singlet-triplet energy gap is too small, thermal energy easily drives the molecule back to the singlet state, losing the opportunity for photolysis. Direct cleavage requires precise alignment of the triplet wave function. For successful cleavage, the triplet state must connect to a dissociative reaction coordinate, as seen in the N-pi triplet state. A pi-pi triplet state can be a trapped state. Photoredox electron transfer rewards both singlet potency and triplet patience. The long-lived triplet compensates for lower driving force by simply outlasting the diffusion limit. TADF compounds leverage small singlet/triplet energy gaps. The triplet charge-separated state, CS3, dictates the reactive yield. The optimal reactive state possesses both triplet spin character and a charge-separated electronic structure, as evidenced by its high quenching constant. Electron spin delays recombination and dictates solvent cage escape. Triplet-borne radical pairs require a spin flip to recombine, which delays back electron transfer and allows for the formation of free ions and radicals. Matrix rigidity and solvent polarity dictate excited state resonance. The environment controls vibrational relaxation and the energy overlap between charge transfer and locally excited states, tuning the rates of ISC, RISC, electron transfer, and back electron transfer. When in resonance, we achieve robust TADF. Long-lived triplet states are highly vulnerable to oxygen quenching. The long lifetime of the triplet, or CS3 state, which enables efficient electron transfer, also provides oxygen with an extended window to destroy the radical generation quantum yield. The definitive blueprint for a TADF photoinitiator involves 5 key requirements. These include efficient formation of a reactive triplet state, controlled RISC, proper wave function alignment, fast-forward kinetics, and spin dynamics that favor radical escape over recombination. While TADF compounds utilize the same cast of electronic states as OLEDs, the design requirements for an ideal photoinitiator are completely different. To design the ultimate TADF photoinitiator, we must purposefully break the rules of OLED design. This video is a first principles guide to molecular design for two-photon absorption, or 2PA. We will explore how to engineer the quantum mechanical transition amplitude to create molecules with stronger 2PA properties. Improving 2PA is achieved by manipulating interactions through 4 fundamental levers. These include maximizing transition dipoles, minimizing energy detuning, maximizing charge redistribution, and forcing constructive interference among pathways. The 2PA amplitude is a coherent sum over actual molecular eigenstates. The key levers for manipulation are transition dipoles and energy detuning, which directly influence the components of the transition amplitude equation. For low-energy 2PA, in a quasi-1D dipolar chromophore, the strength strongly depends on the change in permanent dipole moment upon excitation. This highlights the importance of lever 3, charge redistribution. In higher energy 2PA with resonance enhancement, the denominator of the transition amplitude becomes critical. The optimal condition is near resonant, which relates to lever 2, energy detuning. Care must be taken to avoid issues like sequential absorption. Symmetry reorganizes the eigenstates. Centrosymmetric molecules, such as those with quadrupole and octupole architectures, can place oscillator strength into channels uniquely favorable for 2PA, utilizing lever 4 constructive interference. Push-pull systems operate on a trade-off surface. Maximizing the 2PA amplitude requires a balance of donor-acceptor strength to maximize the product of the transition dipole and charge redistribution terms, balancing lever 1 and lever 3. For strong 2PA, conjugation must remain electronically coherent. It is not just about making the chain longer, but ensuring the electronically active conjugation pathway is both long and coherent, maintaining good orbital alignment. Planarity is essential as it preserves through bond coupling. As the dihedral angle grows, conjugation weakens, and transition dipoles drop, reducing 2PA intensity. Vibronic coupling is a key factor. Molecular vibrations that modulate charge redistribution can lend intensity to a 2PA transition. The best chromophores exploit both electronic charge transfer and favorable vibronic borrowing. Branching requires a coupled core for superadditive growth, leveraging lever 4. If branching simply acts as independent sums, you get molecular bureaucracy instead of cooperative enhancement. The local field amplifies the transition. You are designing the molecule and its environment. Solvents, host matrices, and hydrogen bond networks can dramatically amplify the excitation-induced dipole change. The golden rules of 2PA design involve maximizing the transition dipole moments, increasing the change in permanent dipole, reducing detuning, interfering constructively, and controlling the vibronic structure. Various molecular motifs like push-pull dipoles, quadrupoles, octupoles, metal complexes, and rigidified triphenylamines offer unique advantages for optimizing 2PA properties through their structures. Strong two-photon absorption results from the precise engineering of orbital energies, wave function overlap, and intermediate state detuning. By controlling these factors, we ensure the transition amplitude grows rather than cancels.